Welcome to my channel and I'm glad to see you today. If the dependent variable in your dataset is plotted and it looks like this, it means your dependent variable is normally distributed or approximately normally distributed. This outcome shows that the data is drawn from a population that is normally distributed. It also means that in gathering your data, there was no bias. Therefore, for any parametric test, this set of data will ensure the assumption of normality is not violated. But if it looks like this, or like this, when plotted, it means that the data of your dependent variable is skewed. That is, it is positively skewed or negatively skewed. In this case, your data is not normally distributed. This means that your data is not drawn from a population that is normally distributed. Hence, in gathering the data, there was bias, because there is a deviation from the normal distribution. Therefore, for any parametric test, this set of data will produce a violation to the assumption of normality. On the other hand, if you perform a normality test such as the Shapiro-Wilk test or the Kolmogorov-Smirnov test and the p-value is less than 0.05, it means that there is a statistical significance in the data, indicating that there is a significant deviation of the data from a normal distribution. Such a case will mean that the assumption of normality is violated. So, to move forward, your data has to be corrected to assume a normal distribution so as to satisfy the assumption of normality for any parametric test. The question now is, how can such data that violates the assumption of normality be corrected? This is the objective of this video. So, in this video today, I will be demonstrating how to correct the data that violates the parametric assumption of normality in SPSS. My name is Titocan and this is Titocan Max Solutions, a YouTube channel for improving the knowledge of how to do things. Now, let's begin with the dataset. This data has been fictitiously simulated for the benefit of this demonstration, and it is generated to completely violate the assumption of normality, since our interest in this video is to demonstrate how to correct the data that violates the assumption of normality. This data information is an IQ test score in English language for a set of 30 students in a class. In order to use this set of data to perform any parametric test statistic, the dependent variable in this dataset should be at least approximately normally distributed for the condition of normality to be satisfied. So, before you perform a parametric test with this dataset, the first thing you should do is to check whether the assumption of normality is satisfied or not. To do that, go to the menu bar and click on Analyze. From the sub-menu, put your cursor on Descriptive Statistics. And from the drop-down options, click on Explore to open the Explore dialog box. In this dialog box, your variables are in the box on the left. Please note that for test of normality, you are required to test only the dependent variable. So, as you can see, our dependent variable in this box is the English test score. There can be two or more dependent variables in your dataset, depending on the test statistics you want to perform. Click on the dependent variable English test score to select it, and then click on this transfer arrow key to move it to the dependent list box on the upper right. If you have more than one dependent variable in the box on the left, you can move them all to the dependent list box for the test. But for this demonstration, we have only one dependent variable, and that is the English test score. Now, click on the Statistic button to open the Explore Statistics dialog box, as you can see. Here, the box for descriptives has been checked by default. Ensure that the confidence interval for mean is set at 95%. This default selection will produce the descriptive statistics of the data, including the skewness and kurtosis, which can also be used to determine the normality of data. But I will not be discussing skewness and kurtosis in this demonstration because I have discussed them in great details in my previous video. There is nothing else to do here. Click Continue to close this dialog box. Click on the plus button to open the Explore Plots dialog box. Basically, this is where the test for normality is carried out. In the box plot section, check the radio button for none because you don't need the box plot information. In the descriptive section, uncheck the box for stem and leaf because you don't need that information too. And then check the box for histogram. This selection will produce the plot of the dependent variable as histogram to visually indicate whether the dependent variable is normally distributed or skewed. Then check the box for normality plots with test. This selection will produce the p-values for Kolmogorov-Smirnov test and the Shapiro-Wilk test respectively, as well as produce the QQ plot. Click Continue to close this dialog box. The last button to open here is the Options button. Click on it to open the Explore Options dialog box. This dialog box is where you inform the SPSS system if your data contains some missing values or missing data and the way you want the missing values to be fixed. You can choose one from the 3 options here. But since my data for this demonstration doesn't have any missing value, I will therefore have nothing to do here. So I will just go ahead and click Continue to close this dialog box. Like this, we have completed the procedure of testing for normality in SPSS. Now, click OK to produce the results in the output window. As you can see, the results have been produced, and the necessary result output we shall be considering include the case processing summary, the table of test of normality, the histogram, and the QQ plots. Now, let's take them one after another to determine whether the condition for assumption of normality is met or violated. Let's scroll to the first table. The case processing summary table provides the information of the size of dataset used for the test. As you can see, the total number of participants in the English IQ test is 30, and there is no missing value. Now proceed to the table of test of normality. In this table, 2 test results are provided. They are Kolmogorov-Smirnov test and Shapiro-Wilk test. However, for small size of dataset like the one for this demonstration, Shapiro-Wilk test is most appropriate. If the p-value of Shapiro-Wilk is less than 0.05, it indicates that there is a statistical significance and therefore the assumption of normality is violated. But if the p-value of Shapiro-Wilk is greater than 0.05, it indicates that there is no statistical significance and therefore the assumption of normality is met or satisfied. But as you can see, the p-value of Shapiro-Wilk is 0.000 and is less than 0.05, which indicates that the assumption of normality is violated. If you choose to also look at Kolmogorov-Smirnov test result, even though it is not very suitable for small size of data, you will see that the p-value is 0.003, which is also significant, indicating a violation of the assumption of normality. This means that the data needs to be corrected to gain normality. Now let's proceed to the histogram. If the histogram does not look like a bell shape or is skewed, then it indicates a deviation from normality. Now, let me quickly add a distribution curve to this histogram. As you can see, this histogram is skewed to the right, meaning it is positively skewed, indicating a deviation from normality. Therefore, something has to be done to correct the skewness. What information does the QQ plot carry? Let's take a look. For a QQ plot, if the data points are not aligned or relatively aligned to the straight line, it means that the data is not normally distributed, and therefore the assumption of normality is violated. As you can see, the data points here are not aligned along the straight line, so the assumption of normality is violated by this information. As you can see, this data completely violates the assumption of normality. So what is required at this point is to look out for how to correct this data in order for it to be normally distributed and therefore meet the assumption as required. One of the basic ways to make this correction is to apply transformation to the dataset, and there are 3 typical ways of transforming datasets that violates the assumption of normality. They are 1. Log transformation, 2. Square root transformation, and 3. Inverse transformation. You don't necessarily have to perform all the 3 transformations, for your data at the same time, like I am going to do in this demonstration. These transformations have conditions for application. For example, if the distribution of your data is greatly skewed, you are advised to perform the log transformation. If the distribution of your data is moderately skewed, then you can perform the square root transformation. And if the distribution of your data is severely skewed, then you can proceed to perform the inverse transformation. However, if you perform one of the transformations and the transformed data satisfies the assumption of normality, then there should be no need for you to perform any other transformation regardless of the condition. But in reality, you must state in the body of your research work the type of transformation you use to correct the data if your original data had violated the assumption. However, I will perform these transformations one after another and thereafter check for normality with the transformed data to see if the condition for normality is met. If, however, the transformed variables or data still violates the assumption of normality, then you might have the need to proceed to use non-parametric test statistics for your analysis, if and only if the data also violates the other assumptions for the parametric test. Now, let's start with the log transformation. In most cases, the log transformation is used to correct data that are greatly positively skewed because the log transformation is used to stabilize variance in the data and reduce the skewness, making the data more normally distributed. By applying the log transformation, the skewed data becomes more symmetric, thus meeting the normality assumption required for the parametric test. To perform this transformation, go to the menu bar and click on Transform. From the submenu, click on Compute Variable to open the Compute Variable dialog box. Here, the first thing to do is to give the new variable that is going to be created a name. So go to the Target Variable column to enter a name of your choice. Let's call it log_English since we are doing log transformation. Then go to the Function Group column and click on Arithmetic. And just immediately, the column for function and special variables becomes populated with the necessary functions. Please note that if the distribution of your data is positively skewed, the required function for the transformation will simply be log to the base 10 of x, where x is the dependent variable. But if the distribution is negatively skewed, the required function will be log to the base 10 of open and close brackets maximum s plus 1 minus x, where s is the dependent variable. Since the distribution of the dependent variable for this demonstration is positively skewed, look for log to the base 10 function and click on it to select it. Then click on this transfer arrow key to transfer it to the numeric expression box at the top. As you can see, there is a question mark inside the parentheses attached to the log 10. The question mark is requesting you to enter the variable you want to transform. So go to the box at the left and click on English Test Score. And then click on this transfer arrow key to transfer it to replace the question mark inside the parentheses, as you can see. At this point, click OK to produce the new variable called log_English. The SPSS system has added the new variable to the data table in the data view window. You will see it when you return there, but for now, let's proceed to perform square root transformation. Square root transformation. In most cases, the square root transformation is used to correct data that are moderately positively skewed because it involves a procedure for converting a set of data by replacing the data by its square root. Using this transformation, homogeneity of variance is attained by the dependent variable. Similarly, by applying the square root transformation, the skewed data becomes more symmetric, thus meeting the normality assumption required for the parametric test. As usual, go to the menu bar and click on Transform. From the submenu, click on Compute Variable to open the Compute Variable dialog box. Click on the Reset button to clear the entry columns. Give the new variable a name. Let's call it sqrt_English since we are doing square root transformation. Then go to the Function Group column and click on Arithmetic. Again, please note that if the distribution of your data is positively skewed, the required function for this transformation will simply be square root of x, where s is the dependent variable. But if the distribution is negatively skewed, the required function will be square root of open and close brackets, maximum s plus 1 minus x, where s is the dependent variable. Now, look for sqrt function, which is actually the short form of square root, and click on it to select it. Then click on this transfer arrow key to transfer it to the numeric expression box at the top. As usual, there is a question mark inside the parentheses. So go to the box at the left and click on English test score, which is the raw variable data we are transforming. And then click on this transfer arrow key to transfer the variable to replace the question mark inside the parentheses. At this point, click OK to produce the new variable called sqrt_English. Again, the new variable has been added to the data table in the data view window. Now, let's proceed to perform inverse transformation of the same variable. Now, inverse transformation. In most cases, the inverse transformation is used to correct data that are severely positively skewed. Similarly, by applying the inverse transformation, the skewed data becomes more symmetric, thus meeting the normality assumption required for the parametric test. To perform the inverse transformation, go to the menu bar and click on Transform. From the submenu, click on Compute Variable to open the Compute Variable dialog box. Click on the Reset button to clear the entry columns. Give the new variable a name. Let's call it IMV_English since we are performing inverse transformation. Unfortunately, there is no inbuilt function for inverse transformation in SPSS. What you will have to do for this inverse transformation is to manually enter the function in the numeric expression column. So enter 1 divided by open and close bracket, then go to the box on the left and click on English test score, which is the raw variable data we are transforming, and then click on this transfer arrow key to transfer the variable to the open and close bracket. Then enter +1. The reason I included the +1 to the function is to avoid having error, especially if the denominator is 0. If the distribution of your data is severely negatively skewed, the required function will be 1 divided by open and close bracket, maximum s plus 1 minus s, where s is the dependent variable. Now, click OK to produce the new variable called IMV_English. Again, the new variable has been added to the data table in the data view window. However, in my opinion, I will advise you to use this inverse method only when the distribution of your data is severely skewed. Since we have demonstrated the 3 modes of transformations, let's return to the data table in the data view window to see all the new variables we have created through transformation. As you can see here, we have log English for log transformation, square root English for square root transformation, and inverse English for inverse transformation. Now, let's check if the 3 transformed data satisfy the assumption of normality. To do this, go to the menu bar and click on Analyze. From the submenu, put your cursor on Descriptive Statistics, and from the drop-down options, click on Explore to open the Explore dialog box. In this dialog box, your settings are still intact. Go ahead and click on Reset to clear the dialog box for a fresh start. Now, select all the 3 transformed variables, and then click on this transfer arrow key to move them to the dependent list box at the upper right. Now, click on the Statistic button to open the Explore Statistics dialog box as you can see. Here, the box for descriptives is checked by default, and therefore, there is nothing more to do here. Click Continue to close this dialog box. Click on the plus button to open the Explore Plots dialog box. Basically, check the radio button for none, uncheck the box for stem and leaf, and check the box for histogram. This selection will produce the plot of the transformed variables as histogram to visually indicate whether the new dependent variables is normally distributed or skewed. Then, check the box for normality plots with tests. This selection will produce the p-value for Kolmogorov-Smirnov test and the Shapiro-Wilk test respectively, as well as produce the QQ plot too. Click Continue to close this dialog box. Since there is no missing value or data in the new variables to address, there will be no need to open the Options dialog box. Now click OK to produce the results in the output window. As you can see, the results have been produced. Accordingly, the case processing summary shows that there are 30 participants and there are no missing values. In the test of normality table, the p-value for Kolmogorov-Smirnov test and Shapiro-Wilk test are different from the p-value we had before the transformation. Like I said earlier, if the p-value is less than 0.05, it means that the assumption of normality is significantly violated. But if the p-value is greater than 0.05, it means that the assumption of normality is met or satisfied. So as you can see now in this table, the p-value of Shapiro-Wilk for log transformation is 0.528. For square root transformation, it is 0.141. While for inverse transformation, it is 0.400. All of these p-values are greater than 0.05, which indicate that the distributions of the transformed data are normal, thereby satisfying the assumption of normality. Similarly, for Kolmogorov-Smirnov test, the p-value for the 3 transformation is 0.200 respectively, which is also greater than 0.05, indicating that the transformed data satisfies the assumption of normality. Now, let's take a look at the 3 histograms to determine whether the transformed data are truly normally distributed or skewed. Now, let me quickly overlay the distribution curve for each transformed variable. As you can see, the curve looks like a complete bear shape, indicating that the data is now normally distributed or approximately normally distributed. Similarly, the QQ plots, as you can see, have majority of the data points along the straight line, indicating that the data is now approximately normally distributed. So, the transformed data can now be said to be drawn from a population that is normally distributed, and therefore, the transformed data can now be used for any proposed parametric test statistic. But if any of the 3 transformations was not able to correct the data to meet the condition for assumption of normality, then you will have to use non-parametric test statistics for the required analysis. Fortunately, in this demonstration, our expectation is met. Please note that the data I used is simulated for the purposes of this demonstration, so we have all the transformed variables satisfying the assumption of normality. But in real life, the 3 transformations may not work perfectly for your real-time data. Apply the transformation that help you achieve your desired results. This is how to correct the data that violates the assumption of normality in SPSS, and I hope you will be able to replicate this procedure to correct your own data. But right now, we have come to the end of this video. If you like this video and you want to see more video contents like this, please like this video by giving it a thumbs up, share this video, and subscribe to my YouTube channel to receive notification every time I publish new and useful content. Subscription is free. Thanks for your time and subscription. Thanks for liking and sharing this video, and I hope to see you again in my next video. Bye.